Hey guys, welcome to Safi Next. In this video, I am going to talk about the eigenvalue spectrum, eigenspace, non-degenerate and degenerate eigenvalues of operators. In quantum mechanics, observable or physically measurable quantities are represented by operators, and every operator is in fact a square matrix. The eigenvalue spectrum of Hermitian operators say A is a set of real numbers which is represented by putting the real numbers inside the curly brackets, and I'm writing here the small caps with the subscript I. So the eigenvalues of an operator A is in fact a set of eigenvalues A sub I which satisfy the relation we write in the form of operator A times phi sub A of a variable which I am writing here as x equals small a sub I and the same function phi I of x. This equation is called eigenvalue equation, and the subscript I is in fact a number such as I equals 1, 2, 3, etc. and it represents the length of the set of eigenvalue spectrum. For example, if the subscript I equals 1 and 2, then the operator has two possible eigenvalues and the set of eigenvalues is written as A1 and A2 enclosed inside the curly brackets. Similarly, if the subscript I equals 1, 2, and 3, then the set of eigenvalues of the operator are 3 and it is written as A1, A2, and A3 enclosed inside the curly brackets. The function phi sub ix is a special function in the sense that when it is acted upon by the operator A, it gave rise to a multiplicative number and reproduced the same function. Such functions are called the eigenfunctions of the operator, and the set of eigenfunctions which I am writing here is phi sub x enclosed inside the curly brackets is called the eigenspace of the corresponding operators. So the eigenspace depends on the order of the matrix. If A is a 2 cross 2 matrix, then the eigenspace is two-dimensional and we would have two possible eigenfunctions. Similarly, if the operator is 3 cross 3 square matrix, then the set of eigenfunctions consists of three functions, and we say that the space of the operator is spanned by three eigenfunctions. If we know exactly about an operator, we can find the eigenspace and the set of eigenvalues by solving an equation that we call eigenvalue equation, and is written in the form determinant of operator A minus the eigenvalues times identity matrix, and the whole of this equal to 0. Obviously here I is in identity matrix whose order equals the order of the operator A. Now if every eigenvalue Ai in the set of eigenvalues corresponds to a distinct eigenfunction, then the eigenspectrum is called non-degenerate spectrum. For example, if we have a situation like A applied to phi 1x gave rise to A sub 1 phi 1x, and if A applied to another function phi 2x and it generates another eigenvalue a small a2 times phi x and so on, then the eigenspectrum A1 and A2 is called non-degenerate eigenspectrum. On the other hand, if a given eigenvalue corresponds to two or more than two eigenfunctions, it is then called degenerate eigenvalue. For example, if A1 corresponds to two different eigenfunctions, which means if the operator A applies to phi 1x and it produces A1 times phi 1x, and then operator A applies to phi 2x and that also produces the same eigenvalue A1 times phi 2x, that is, the single eigenvalue A1 corresponds to two different eigenfunctions, then A sub 1 is called non-degenerate eigenvalues, or in other words, we say that eigenvalue A1 is twofold degenerate. Similarly, if A1 corresponds to three different eigenfunctions, that is, if the operator A acts on three different eigenfunctions and every eigenfunction produces the same eigenvalue, then that corresponding eigenvalue is called threefold degenerate. And then, if you haven't yet subscribed to Safi Mix, kindly extend your favor by clicking the subscribe button to support the channel. Thanks for watching.